Good afternoon. Thank you for joining us on our Premium Support webinar. We will be hearing from Dr. Brett Malone, our VP of Business Development, and he'll be presenting on the use of model-based systems engineering for infrastructure planning, modeling dynamic systems for real-time monitoring. As we go through the presentation, we would be happy to answer any questions online or off, depending on the nature of the question, following the presentation. So please type your questions into the chat box, and we will answer them directly following Brett's presentation. And with that, I'd like to turn things over to Dr. Malone.
Thank you, Gina. Thank you, everyone, for joining and attending. My name is Brett Malone, and I'm pleased to talk to you today about how to apply model-based systems engineering approaches to maybe a more relevant problem that we're facing in a lot of our cities and across the nation in terms of our infrastructure. And so what I'm going to do is talk today a little bit about infrastructure planning, and in particular we're going to go through an example that talks about some of the traffic management and city management. The important part of this, however, is not the example problem, it's how to apply these modeling protocols for building dynamic systems and how to use those models to derive most important information. You may have seen on the standby screen that we're also promoting and encouraging all attendees to join us in Chantilly, Virginia on October 12th through the 14th for our user conference. We're going to be walking through a lot of use case studies. We're going to be looking at a lot of case studies, and we're going to be studying some of our latest architecture as well. And it's going to be an exciting time for users. It's going to be an exciting time for new folks who are just getting into model-based systems engineering and want to learn more. We're going to have some great speakers from Booz Allen, from the DoD, and a lot of our own engineers will be there to answer your questions. So let's get into the topic today. We're going to talk a little bit about just the drivers and how we see model-based systems engineering primarily supporting an architecture study. So we're going to use a very simple example, as we talked about, a traffic management system, but we're going to overlay the model-based systems engineering approach so that we instruct along the way. And so that way this MBSE approach can be relevant for maybe a problem you're working on today or this week or this month. We're going to talk a little bit about some of the areas that you can apply it, and then as we mentioned, feel free to ask some of your questions on the chat box. We'll get to as many as we can, and we'll get to them as time permits. And we also, at the end of the webinar, we will show you our link to our community website, and we'll be able to show some of the ways that you can interact with other users and generate your own discussion forum on these particular topics. So I'm going to start with the end and give you an idea of how we're going to summarize this talk, so that along the way you'll be able to look for these clues and pick up how the story fits together. But most importantly, we're going to talk a little bit about how to apply this MBSE approach, model-based systems engineering. So most of the talk is going to be focused on how to build this model and then exercise it. So some of the key advantages that we're going to talk about at the end will be how to use this model to understand the boundaries and support project management, and even in particular, specifically subcontracting. So how can you develop protocols, system specifications, cost justification, all the necessary analysis needed to properly plan a project and then properly kick it off and manage it throughout the life cycle. We're going to talk to you about how to use a dynamically built model to run trade-off studies. These are the bread and butter of understanding the sensitivity of constraints requirements. So we're going to talk about trade-off studies to set thresholds, to set requirements, and to properly scope the project and bound it. We're going to talk also about cost management, and in particular, how to use a model-based approach above and beyond a document-centric approach so that you can really understand these cost drivers. And then finally, as we've talked about already, the documentation and generating the documents so that you can provide traceability. These are key items that we're going to summarize, but I wanted to get them right up front as an introduction. So let's first discuss what is meant by model-based systems engineering And we'll do that by basically comparing it against a document-centric approach, which we're all familiar with, a very static approach. It's a very somewhat linear approach, and it can be quite cumbersome as the scope of your project grows. So the first point about comparison between a model-based and a document-based approach, we're building traceability into our model. So by building relationships, and we'll discuss what that means in a minute, but by building the connection points between data in your model, we're naturally building in traceability. So it's not an afterthought, it's not a nice to have, it's necessarily a, it's a byproduct of the model approach. We also have one model and many views. And representations is another word for views. It's another word for diagrams. So without getting hung up on one particular diagram, the idea is that a dynamic model built properly can give you multiple views without having to redraw the information. In a document-centric approach, you're typically drawing and redrawing diagrams to try to represent what your model or what your system is trying to accomplish. With a model-based approach, you build the model once and then you extract your views that you need. And then finally, a model is executable. Unlike a Word document with hundreds of pages of paragraphs of text, a live document, a live model creates a dynamic decision-making environment, and we use our simulation engine to take advantage of that. So just 3 tenets that compare model-based centric approach, and without getting the sense that model-based systems engineering is complex, it's important to understand the fundamentals. So it's entirely a simple concept, and it's built on these constructs. This concept of these entities and relationships. In other words, information that's linked together. And again, these aren't novel ideas, but when you put them together, they form a very powerful way of solving problems. The other thing that's important is in a modeling environment, and in particular in Vitech's approach, where we have a methodology that allows you to start anywhere and iterate. This is the way projects start. Rarely does a project start at the beginning and progress in a very linear fashion throughout a logical progression. Typically, you're iterating, you're going back and forth. You start in the middle, maybe you're redesigning. So being able to layer designs and start anywhere is important. And also being able to understand that document creation is the output of a model. It shouldn't be the process. Too many times we get hung up on the act of creating the documentation, and we fail to understand that we need to be able to generate the documents from our analysis, not generate the document as a necessary evil, if you will. So I'm going to put these concepts together in a very simple model, and it's going to be a traffic monitoring system model. Now this would be what you would typically expect from a large municipality who might go out to bid for a complex architecture to manage the traffic, to manage the alerts, to manage the emergency response, and to manage the overall system. Now, if any of you were at the INCOSE session, you may have seen some of this presented as a vendor expo where we showed how to solve this problem. So you may have seen some of this information, but in particular, let's lay out what we're talking about. So we start typically with a concept of operations, CONOPS, where you're going to have an engineer sit down with a customer and a project manager, and they're going to say, hey, what does this thing have to do? What do we have to accomplish here, and how do we capture that? So, we look at the logical layers, we look at some functionality, and you're going to start peeling back, oh, well, hey, we need to understand what the operators are going to do with the information. We need to record the information. We need to have input devices. So we're going to have cameras on stoplights. We're going to have consumers or users of the data, and those consumers are going to have many different devices, maybe handhelds, maybe wireless, maybe they're going to go to a website. And then we're going to have, emergency response people who need to leverage that information to make decisions about routing information, notification, potentially disaster recovery. So typically this would be captured, let's say, in a requirements document that your customer or that you may start to develop. And this is really where the process starts. So again, you know, this challenge, this vendor challenge, if you will, starts with a very brief description of what do we have to accomplish, very high-level requirements. Now that by no means has that captured all of the necessary detail, but it starts to frame out our concept of operation. So let's take a break for a minute from the example and talk about now how does our methodology and our approach start to fulfill that analysis. So our methodology is based on two principles. One, that we follow a layered approach. In other words, we construct the model in layers of increasing complexity. And you know, we don't go too deep in any one domain before we make sure we hit all the domains. Now, what do we mean by a domain? So the second concept that we really talk about is the fact that we manage multiple domains from a centralized model. Now, this is not a PDM system where you have product lifecycle management data. I mean, this is a centralized model that's main focus is to capture the essence of your system in 4 very important domains. The first is what we just talked about, the requirements management. The second is the functional domain, the behavioral analysis. How do the components relate? Third is the architecture synthesis. In other words, now that I understand the functionality that has to happen in the behavioral domain, how do I start applying those functions to physical components? And then the fourth domain is what we talked about early on, the simulation. How do we verify that, yes, indeed, we have captured the important functions and they all hang together to accomplish the necessary functionality of the system? So the simulation is very important to fulfill verification, validation and verification. And as we talked about, we can iterate across these domains. Well, we do that with our product called Core. So in order to bring this to ground and in order to bring this model to life in an actual software system, we provide Core as the main tool that integrates all of these domains. So what we just talked about in terms of the conceptual model for these layers and these domains is facilitated in the software system Core that makes sure that all of your information hangs together and traces accurately. So you can see the requirements domain, the requirements generation is developed, and the behavior domain, the functional analysis, the functional decomposition is developed in the next layer. We start to add components in the architecture domain, and then we can start to add state diagrams. We can start to add and understand components and component breakdown diagrams. And then the V&V domain sort of brings it all together and demonstrates and shows the simulation of the system, so the functional simulation. We're going to show each piece of this now as we return back to our model. Now, just again, one quick side. This is the interface for Core, and what you'll notice is that we've logically organized this information into a simple set of folders and a simple set of elements that can be added and managed in a very logical schema or a very logical database mapping. So the interface for the model becomes these various views or representations. So as we look at the hierarchy diagram for these set of operating conditions, you can see that we can logically break them down in view. So Core is a very solid, very stable interface. We're on our 7th version, and in October at the user conference we'll be releasing and announcing really exciting new functionality for Core version 8 that really has added a lot of capability in many different ways around the software. So let's come back to the requirements, and we're going to start into our problem now. And as we talked about, the requirements are generated from sources. We use Core as our tool to be able to onboard these requirements into the model and into the tool. So again, looking back into our diagram, or looking back into our document that has captured these key requirements, we can start to decompose what do these requirements mean. So this is our decomposition. At the highest level, you'll see that we have to identify the traffic and identify levels on all highways and all thoroughfares. Well, that's a very all-encompassing requirement, so it's nice to be able to break that down and decompose it. Now, we're not going to go into the details of each box, but you can see we use this product and we use this methodology to start decomposing not only the requirements, but you can see we have particular functions, we have particular use cases that satisfy these requirements. So when we get into the concept of entities and relationships, well, this mapping shows the relationship between the entities and in their diagram. We now might want to go and look at the components that would be that would generate or that would create the system for us. So these components in the physical diagram would break down logically into, say, an overall management system. You're going to have operators, you're going to have consumers of the data, your end users, and you would also then be able to decompose this system into smaller systems and subsystems of components. And we can logically describe the physical context in the block diagrams. And you can see we manage the numbering of each of these components. We manage the linkage between the systems and the subsystems, and we manage the relationships between what type of subsystem they might be, whether this is a facility, for example, whether this is a human, for example, or this is an overall context diagram. Now, another important part of this is, for this particular problem, what's important is that it's decomposed properly so that we can build the interfaces in an appropriate way. And if you look at the interface diagram, you start to see now we can represent the details of what has to go between these systems and these subsystems. So the computer link, the main panel linkages, the monitors for the video surveillance, all of this information has to be represented. And if I can go back a step, typically what you'll see in a document-centric approach is the documentation of the deep documentation of the physical components. But traditionally you'll see in a document-centric approach there's a failure to properly define the interfaces. This is where a lot of problems occur, and this is where a lot of other methodologies really fall short, because the correct definition of the interface can make or break your system, because we're very much a black box centric approach and environment, and we give too little thought to the proper definition of interfaces. And a lot of times you don't realize it until you're way down the road and you have severe incompatibility problems. And a lot of times that will force you to use only a fraction of the capabilities of your system components, because you just can't work with them, you can't get the data you need into them or out of them, or maybe they just don't support the bandwidth that you're generating. So being able to logically describe the flow and the interfaces becomes a critical aspect of this model. Now that we've done that, we want to then start to put together the system activities. Well, what kind of events, what kind of triggers are going to happen? What kind of actions do we take upon those triggers? Who's making those triggers, and so forth. So you can see we can generate this this activity diagram basically in a way that defines very easily the routes and the passages through each function. Now, the reason this is helpful for us is it gives us a picture of what may not be happening, or it may give us a picture of where there's redundancy, or where we need to add redundancy. So in other words, if we're collecting data from one set of sensors, we may realize that, well, if this sensor goes offline, do we have another alternate route for this sensor information? Well, maybe we can get it through the video surveillance, for example. So being able to use this model, dynamically modify it, and test your assumptions throughout the process, that's really the critical part. So the fact that we can add these components and associate these relationships and start to generate the functional flow or the activities through the process starts to give us an idea of who has to do what, when do they do it, and how will that information be fulfilled. So emergency responders are down here, for example. We need to get those alerts, we need to have the reports, and we need to have the accident response all linked together. So for example, if the linkages were not here, we would flag that as a deficiency, go back into our model, and quickly add that so we can add that connectivity. The use case diagrams are also very helpful in understanding, well, how will this system fulfill the end user who wants to understand the traffic report, and what do the operators have to do to interact with each system to fulfill that data need. So again, the use case scenario satisfied by the model in the modeling environment can provide you with a picture of how will the system be used and who will use it. Now, one of the important parts about a document-centric approach, people spend a lot of time creating these diagrams in very static environments. And if your system is small, that's okay. And if your system is very, very well defined and you've put a lot of whiteboard thought into it and you've gone back and forth, that's okay. What we find is that typically you're going back to the drawing board more often, and it's not after the first layer. It's when you start adding some details and you start trying to hang the whole system together that you realize, hey, we forgot a very important part of this use case. For example, how do we support this wireless capability, or how do we support this information that we have an end user we hadn't considered? So typically a static-based approach would, once again, you would have to go back and literally erase the lines and redraw and hope that you've got it right the second time. With a model-based approach, these diagrams are generated from information you're connecting. So these diagrams become generated on the fly as you refine your model. So just a final thought on what we would call these functional modes, and in particular the transfers. Being able to understand how do the sensor operations represent different states. So this diagram representing the states of a sensor really gives you more resolution in your model. So for example, functionally, if I want to go through in a test mode, I can do that. I can select the sensor, I can hit the test function, and I can go through my routing. If I'm in normal mode, obviously I can be in receive collect data mode. And then if I want to shut the system down or be in the off mode, we know what functions handle that. So again, if you're not considering the details and the resolution in your model, you may miss a very important point of where the vendor, you may make it a requirement for your vendor that they have a test mode. Well, if you can't model that function, or if you can't represent that, then we don't want to miss important details or fidelity in the model. So again, as you go along, the importance of a model-based approach is that you can really add the fidelity and the details of this guy. All right, so now let's talk a little bit about what we would call risk management and managing issues. One of the keys in developing a proper set of and scope of requirements is the fact that you can map issues back to them. You can map a lot of information and connect the information in meaningful ways. So for example, we have a requirement that we must be able to handle these major traffic incidents, and we need to label what might happen. So for example, you have an accident response time. There's risk and uncertainty involved. A major traffic incident is, could cause a risk in the accident response time. Now the use case, you can see the use case, which is, why do we have that use case? So we have this basis of relationship linking back to the requirement. And so, for example, why would we have that, and what's the relationship? So here it's very clear. We developed this use case, the use case of incident response, in order to fulfill, and that's based on this requirement of being able to handle these traffics. Now we also have, for example, an issue. We have major traffic incidents that could be happening, and then we have the risks of these guys happening, and we may route and weight those. In a parametric model, we can do that. Okay, so now let's bring it together and now verify what's happening, and talk a little bit now about how to execute the model. A lot of what we've talked about up to this point has been focused on building the model, accurately capturing the functionality, being able to define what the actors do, and being able to define the use cases against the requirements. And that's all very important, and we go through several versions of that. But it really, until you can exercise the model and verify that we've handled these cases, you're still somewhat left up to implementation. So we don't like to chance the implementation. We would prefer to simulate what we think is going to happen, and we fully expect and hope that, hey, the simulation is going to highlight some weaknesses that we can come back around on our system and optimize. So part of the validation, part of the V&V is, yeah, understanding that we've checked the boxes, but more importantly, it's understanding, hey, where are the places where we can really get the most performance out of this? Now, that's where the simulation really comes in handy. So let me walk through this case and talk about the simulation, and let's pull out a particular example that we can all relate to. So in our design, we have IP devices. We have cameras that are mounted on traffic lights, and they require a certain amount of bandwidth to stream the output. And that's driven by network performance, security. These are all issues. So consumers of this data have certain bandwidth requirements. The data for generating and populating that information is driven by these devices in terms of the information that they can stream. So we have a chain of requirement, if you will, and we have a model that we can test and we can simulate. So inside of Core, this is a screenshot from our Core software that demonstrates how you would use our simulation. And this simulation takes the functional model that we showed earlier. If you recall, the functional model that walked through each box and showed when an event was triggered, it showed who triggered the event, what the response was, and what the consumer would receive as a result of that trigger and that response. So what we've done is we've taken that functional model, we've brought it to life in our simulation by walking through functionally each block, and we've looked at inside the block, we've looked at the parameters that are driving that information. And we do that because we want to understand what are the drivers, what are the numerical drivers that get us to a certain threshold. In other words, what we're trying to do is to demonstrate in very simple terms what are the bandwidth requirements for this system. And it's an easy question to ask, and in some document-centric approaches, especially if you're sitting around a conference room and you're whiteboarding this guy out, if somebody asks the question, what are the bandwidth requirements for this system? Well, it's easy. You look at your biggest consumer of bandwidth and you say you just peg it at that point, right? Well, it's not quite that easy, because you could have layers, you could have redundancy, you could have events that are triggered in parallel. So you can have a lot of details that go into what might seemingly be a simple question to ask. Well, we use the simulation to give you a very precise answer. And we use the simulation to make sure that you understand what are the drivers for this issue. So let's decompose what you're looking at. This is, again, as I said, a screenshot from the simulation that is looking at the bandwidth resource. Let me go back for just a minute. And understandably, you know, we would have consumers of this information that would be pulling, and we could measure this at various load times and really take a look at what's required. But so resource is our bandwidth, and we use this actually as a variable that we can change and update depending on particular system parameters. We also look at the functions and the steps that we're doing, the triggers, the sensor returns, the track files, the traffic reports, the accident response direct, reviewing the traffic data, providing the video, the emergency response. So each one of these systems and each one of these functions contribute to the utilization of bandwidth in some way. And you can see that we have red bands in some of our measures for our resource. So as we walk through the simulation on a time scale, across the top this is time, we run the system out over a period of time, and then we look at, say, the impulse of a data pool. And you look at the collect data part of this, and you can see that we're starting to peg the system. This is just a simple deficiency in our bandwidth. Well, if I go to our next system, what I've done behind the scenes is that we've refined the requirement and we've set a new threshold for the bandwidth. So moving our bandwidth from this level, and this level might represent, let's say, a 20 meg pipe, depending on the city, depending on the model. It really, the specific numbers don't matter as much as the fact that you can parametrically adjust these. But if we look at this parametrically, we see now the same simulation runs with no bottlenecks. And this is what you want, especially when you're looking at critical systems and critical infrastructures. So as I look at the comparison between the simulations, I can go back to my vendors. I can go back to my budgeting committee, for example. I can go back to my customer, and I can say, look, we need to set this bandwidth at this threshold because that satisfies this simulation that we verified. So now you have hard, tangible data that supports your need for that threshold and that requirement. And this is a very critical piece of the story. And it's something that's very difficult to do with a document-centric approach. It's very difficult to do with static systems. It's just very difficult to do when you have disparate data sources and you have different hardware and software, different software tools that you're using in your system and design process. So what we like about this approach is the fact that everything's unified, and most importantly, the executable nature of the model allows us to do studies that we could never do before. And this is important regardless of what industry you're in, because regardless of where your system lives, you need to explain to your customer the trade space. You need to explain to your vendors why their requirements are so critical. And if you can't put your system at that margin, and if you can't put that system in the threshold of cost and performance, regardless of what the items might be, you know, this might be bandwidth, this might be certain elements, but you know, if you look at cost as an independent variable, and as we march up this cost trend line, your system will soon reach a point at which there are diminishing returns for throwing more money at the problem. And importantly, you want to be operating in this zone where, you know, a few more dollars gives you the best bang for the buck. You don't want to be operating in this flat zone down here where, you know, you're able to generate a lot more performance with just a few more, you know, it takes a lot more dollars in this flat zone. But over here, a few more dollars in the middle of the curve generates the highest return on investment for performance. Well, let's bring this story back around and talk about what do you do next. And most importantly, no one vendor, no one company, no one group really does everything anymore. You know, rarely do you find a situation where you don't have to go out with a system spec. You have to go out to vendors and ask for RFPs, and you have to generate what's a defined representation of what you want built. Well, this is an example of a document that's generated directly from CORE, and as you can see, this is a document that was prepared from this traffic management system model. So this was all neatly formatted, neatly tabled, indexed, and each section in this diagram, each section in this document represents and tells the story of what's in that model. And so it's important to be able to generate this document because this is what you would have to give to your customers. This is what you'd have to give to your vendors who are going to build this system. If you're going to manage this project, you need this. And it's important to have it in a consistent way that's always consistent with your model. Now, the other item that you might want to come around on is say, hey, have we answered the mail? So have we done the verification against these requirements? And so a typical system engineering process we can also generate the traceability matrix. In other words, in our documentation, we can very cleanly and easily generate very simple reports that will verify for your customer and verify for your vendors that we've traced all of the requirements back to a key element in our design. Or, if we have not, we've highlighted them and we've explained why. So the verification and the cross-referencing of requirements, system elements, components, and architecture is absolutely critical as you move from a design and conceptual phase to a more detailed and implementation phase. So, we should not overlook the importance of traceability, but, again, traceability is a term that's waved around too nonchalantly, and it means something, and it shouldn't be used in a very cavalier way. Traceability can be shown very clearly and very plainly in this kind of document that's generated from a model in a modeling approach. So again, the output of a highly connected interdependent model forms very important documentation that can be kept up to date very easily. The other thing that really gets people, and this is something that comes back around and bites a project maybe midway through, is the concept of configuration management. In other words, being able to track what changes were made, who made them, and what were the changes. And it's the simplest concept, and yet sometimes it can be the smallest thorn in the side of a major project that brings it to its knees. So if you follow a model-based system engineering approach, if you follow a modeling approach, if you follow a centralized approach, we can provide for you the capability of managing traceable configuration changes. And this is important because you want to be able to show, hey, somebody somewhere down the line changed the response time for major traffic incidences, and it was 5 minutes. Now we're looking at it in 10 minutes. We want to know who made that change, because if that has a significant impact somewhere else, or if that change is having an impact, we want to be able to roll back and go find this guy who made this change and have a conversation with him. So configuration management is really important, and traceability throughout your project team is critical. Core software provides that. Any good modeling environment should provide that for you. If what you're using doesn't provide that, you ought to look twice at it, and just consider, hey, are we managing this configuration problem properly? And this is not an inherent problem for traffic management systems. This is an inherent problem for any complex system that you're about to undertake. So I promised you that we would revisit these summary points, and here we are. So the key points that we've talked about, we definitely talked about the model in understanding the boundaries, and in particular project management around cost and the elements of subcontracting, developing a system specification that can be given to a vendor, that can be used for an RFP, that can be used for documentation for the next term, whatever you have. We also displayed and talked about the importance of using the model to do these trade-off studies around threshold requirements. Having a requirement is important. Being able to define the proper value of that requirement, that's the hard part. And you really can't do it unless you can demonstrate the sensitivity of that requirement on the system. And if you take the story a little bit backwards, you can say, look, if we can relax this requirement, if we can relax this parameter, we can give you 20% less cost, or we can give you 20% more performance, whatever the sensitivity is. These are important items that you just can't exercise a Word document to get that answer. But indeed, you can exercise and generate the model to get that answer. Cost sensitivity is the same way. If we can look at the sensitivity of bandwidth, for example, and maybe that becomes a constraint that we impose on the vendors to be able to find the best systems, the best cameras that can operate in that reduced bandwidth environment. It's not always what you want, it's what you have to work with that you need to set as drivers. And then we've talked also about the documentation process. Again, traceability, good documentation, meaningful documentation, and then having an up-to-date model. Those are all important tenets, and if you can pull that off, typically it's done most easily in a unified environment like Vitech's Core, which represents a very centralized, solid approach to solving these problems. Just a quick word about Vitech. We've been in the model-based systems engineering space for many, many years. We provide the software, as you know now, the tools, the support. We also provide a deep bench of professional engineering services that can come in and help you architect that model. We can help you get started by defining, maybe some of the boundaries and some of the domains and some of the initial ways to decompose the problem. And, we're providing a lot of research and innovative new methodologies and that continually fold into the tools. And as I mentioned earlier, we will continue this conversation primarily on our community site. We have a forum that will foster conversations. We hope to see you online in this forum, and we hope to get your comments, your feedback, your questions, anything and everything. We want to be on that conversation. This is by no means a monologue. This needs to be a conversation about how to implement this correctly in our space. And then finally, a reminder again for our user conference, October 12th through 14th, coming up in Chantilly, Virginia. More information on our website, vitechcorp.com/insight2011. Laura's information is here too for registration. I think you'll be very pleased with the agenda, with the level of topics, with the technical discussions, as well as the industry leaders that are going to represent how model-based systems engineering is having an impact in their space. So we're very excited to be hosting this. We're very excited to be hosting some top speakers, and we certainly look forward to seeing you there. So with that, my name is Brett Malone with Vitech. I appreciate your time and your attention today, and we hope to see you again on our next webinar. Gina, I will turn it back over to you to manage any of the questions, the Q&A that we might have, and
Thanks,
we'll
Brett.
take it from there.
I really appreciate it. We just had a couple of quick questions. One came in about how did we assign bandwidth to functions? Was it actually assigned as an attribute?
It is. So that's a good question. And if you look, I'm not sure that we have the right screenshot for that, but each function and element has a particular attribute that we can assign as a property. And it's a great question because bandwidth can become a dynamic attribute, and it could even become a computed attribute, whether it's an input or an output of a function. we can take this to several levels. We can assign it as a static value. We can assign it as a variable that might follow a certain prescribed probabilistic or stochastic format. And then we can go all the way across to generating a script that would provide that as an input or an output for us through some other computed means.
Great.
Hope that answers the question.
Yeah, that was excellent. Thank you. And then just one other question. Is there a way in CORE to check on your models, such as are all of the functions allocated to components?
There is. If you look at the core model, we can run the verifications of, the linkages. So if you look at in the component breakdowns, there's an easy way to decompose your model through the different functional views to get a more complete assessment. So the simulation, for example, would be a way to demonstrate where you have either a missing function or you have a breakdown in your logic. So the enhanced functional flow block diagram, EFFBD, really starts to provide that picture, that formula format for you. So there's a couple ways to do it, and there's a couple ways to really sort of verify how things are all connected. And at the end of the day, when you run the simulation and it will flag that you either have a broken link or you have a function that doesn't have a component represented with it, then there are ways to be able to ferret that out. But that's a great question, and that's really the purpose of doing that V&V. That question is very telling, because that's the power and the benefit of doing the verification, the validation in your process.
Absolutely. Yeah, and we can even take that to a more in-depth level if anyone wants to on the forum, on the community site. So that's great. Thank you. I think at this point those are the questions that we would want to answer online. So if you don't have anything else, we really appreciate everyone joining us today. Thank you very much, and thank you, Brett. That was excellent. Thank you.